All right, so we got about 20 slides left on probability. So some of this you might know, some of this you might not. Okay, so when you do probability, there's these things called sample spaces. A sample space is all of the possible outcomes. So this is rolling a pair of dice. So you can see that the row says, okay, what if the first die is a 1? So then the other die could be a 2, 3, or 1, 2, 3, 4, 5, 6. Second row, what if the first die is a 2? 1, 2, 3, 4, 5, 6 for the second die, and so on, right? Now, the way to determine how many possible outcomes there is called the fundamental counting principle. So in the first die, how many different rolls can you get? Well, there's 6 because there's 6 numbers. In the second die, how many different rolls can you get? Well, there's 6 because there's 6 numbers. If you multiply those, you get 36. And if you count how many pairs of die there are, there's 6 across the top, 6 going down, there are 36. So that's a quick way to get the probability, or not the probability, the sample space of an event. So when you're trying to find the probability, it's simple, right? If you're trying to find the probability of A happening, it's how many times A can occur out of the total. So it's A out of the total. Again, fraction, decimal, percents, those are all ways to answer probabilities. The complement rule. Oh, first of all, so we should know basic rules that the probability of an event is a number between 0 and 1, right? So it's a fraction, but it should not be greater than 1, okay? Or between 0 and 100%. All the possible outcomes together must have probabilities that add to 1. You need to represent 100% of the data at all times, okay? And then there's this idea called the complement rule. If you want to find the probability of something not happening, so the probability of A complement, that is not A happening, you simply need to take 1 and subtract the probability of A happening. Because if you do that, this is saying that A happens. 1 minus A happening gives you the probability that A is not going to happen. So be aware of that. That's called the complement rule in probability. Okay, mutually exclusive. So now we're working on compound events. Say we have 2 events, and we want to find the probability of them happening at the same time, right? Well, if they're mutually exclusive, they never do happen at the same time. So the probability of A and B are 0. They don't happen at the same time, right? And same time, okay? Never occur together. So if we're going to find the probability of A or B occurring, and we know our events are mutually exclusive, that means they have no overlapping outcomes, then we just take the probability of A plus the probability of B, okay? So that's pretty simple. Again, that's if 2 events can occur at the same time. Okay, now what happens if the events can occur at the same time? Well, now you have to do this formula. So the probability of A or B happening is the probability of A happening plus the probability of B happening minus the probability of A and B happening. And the reason is the following. Within the probability of A happening is A and B. Same thing within the probability of B happening is A and B. So you're counting this twice, 2 times. So that is going to usually lead to a probability that's greater than 1, which is a problem. That's why you have to subtract the probability of A and B 1 time so that you don't overcount certain situations. All right, so be aware of that as you look at problems. Okay, so let's take a look at this problem here. It says students in a college statistics class want to find out how common it is for young adults to have their ears pierced. They recorded data on 2 variables, gender and whether or not their ears are pierced, for all 178. The two-way table summarizes the data. So two-way tables are another important idea. So two-way tables have 2 variables on them. So the gender are going to be the columns, male, female, and total. The pierced ear is the rows. Yes, pierced ear, no pierced ear. So each of these boxes represents 2 events, male and having pierced ears, male and not having pierced ears. So be aware of that. And then the 178 in the bottom right corner is the total of everybody. So it says, let's define some events. A is going to be getting a male, so A is male. So over here, I'm just going to put A on top of male. And B is getting a student with pierced ears. So over B, I'm going to put pierced ears. So it says, find the probability of B. Okay, so the probability of B is going to be all the B's, 103, out of the total. And that's the 178. And again, you would divide this, whatever it asks for, but that's the answer, okay? Now, let's find the probability of a male and a pierced ear. So let's go over here. Let's erase this. So we want the probability of A and B. Now, one thing I did not show you is that if you're looking for and probability, this upside down U might also be used instead of the word and. So be aware of that. So where are the males with pierced ears? Well, the males with pierced ears is right here. It's the 19 out of the total 178. Okay, and now what about the probability of A or B? Well, to find the probability of A or B, and again, or is the U. So now we have to look at all of the A's. So all of the A's are 90 plus all of the B's. All of the B's are 103. But now these two events overlap. There are 19 males who also have their ears pierced. Those 19 are in the 90 and those 19 are in the 103. That can't happen. You need to subtract 19. You need to subtract that group once and divide it by the total. Again, say you didn't do the minus 19. 90 and 103 is 193. This cannot equal 193 over 178 because that would be a number bigger than 1. That's not a proper probability. So you need to subtract the 19 and you will get a probability of 174 out of 178. Notice that all that you're not counting is this. You're not counting the 4 females that don't have their ears pierced. So notice that that is the 4 missing. Okay, so again, hopefully this brings to light this idea of the and versus the or. And these are not mutually exclusive because there are males with pierced ears. Okay, so some Venn diagrams. So when you're looking at a Venn diagram, so when you look here, the rectangle is the entire sample space. The two events are each circle. So event A is this yellow circle, event B is the blue circle, and then the outcomes they have in common are the green overlapping region. So this is your A and B. Remember, it's the upside down U. And again, that's what they have in common. So there's your A and B section, the overlap. Here's your A or B. And again, this is A or B or both. And again, remember that this group right here is going to be counted in the A circle and in the B circle. That's why when you use that formula, you subtract it once. Here's a couple special Venn diagrams. So mutually exclusive, remember that means the probability of A and B is 0. That means they don't overlap, no overlap, which is what you see in the picture here. And then the complement. If this circle is A, then you want everything outside the circle within the rectangle. That's the complement. That's the A not happening. So remember, A complement is the not A part. Okay, so let's take a look at this problem. In a large apartment complex, 40% of residents read USA Today, only 25% read the New York Times, 5% of residents read both. Suppose we select a resident at random, make a Venn diagram. So we're just going to do part A. So we're going to make a Venn diagram here. So you start with the both. Remember, this could be, let's let this be USA Today. So A is USA Today, and let's let B be the New York Times. Okay? So we start with the both. 5% read both. 5% as a decimal is 0.05. That goes in the middle. Now it says 40% read USA Today. Within that 40%, or that 0.40, is this 5. So you need to take 0.40 and subtract the 0.05. That is 0.35. 0.35 goes in this section of the A. So together, if you add them together, because they do make the entire circle, together you get the 40% that read the paper. But 5% read both, and 35% read only A. So this is the A only group. A only. Okay? And this is the both. And now we do the same thing with our New York Times. 25% read New York Times, so that's 0.25. But again, 0.05 is included in that already, so we subtract the 0.05, that's 0.20. So 20% read B only. And now there also needs to be a number out here, and that number must be what's left over. Who doesn't read neither of these papers? So we're going to take 1, which is the total, and we're going to subtract 0.35, 0.05, and 0.20. When you do that, you get 0.40. 40% of people don't read any paper, neither of these two papers. So that's how you make a Venn diagram. Okay. All right, good deal. Okay, conditional probability, very important idea. The state test loves conditional probability. So when you're doing conditional probability, you're looking at the probability that one event happens given that something else has already happened. So this is your notation, and that just means B given A. So the biggest thing with conditional probability is that you limit the total. So if you can remember that when you do conditional probability, you'll be golden. You limit the total. You already know something happens. So my example is always in a classroom, right? There's male and female students. Well, if I know that somebody is a male, I don't have to look at the females. I just focus on the males, so that you will cut my total down by a lot. Should increase my probability because I know something about the person in that regard. Here's your formula. So to find the probability of B given A, remember this bar means given. We're going to find the probability of A and B happening together over the probability of A. Think of this as a fraction bar. But in the top, it's A and B, right? Or, yeah, okay? And again, I like to think of it like this. It's probability of both happening over the probability of the given. And again, the given is A. A is the given. All right, so let's take a look at this problem here, okay? So it says Yellowstone surveyed a random sample of 1526 winter visitors. They asked each person whether he or she owned, rented, or had never used a snowmobile. Respondents were also asked whether or not they belonged to an environmental organization like the Sierra Club. The two-way table summarized the survey response. Okay, I read that very fast. Sorry. Suppose we randomly select one survey respondent. Define E as environmental club member. So environmental club member, this is E. S as snowmobile owner, that's S, and N as never used, that's N. Find the probability of N given E. So again, that's given. So the probability of N given E is the probability of E and N over the probability of E. Both over the given. So let's look at the probability of E first. E is here. E total is 305. We are not going to use 1526. We are going to limit the total to just the total of the given amount, 305. And now to find E and N, we have to use E and N. Here's N. Just slide N over to the E column, and there's your 212, and that's your top number. And this is how you find conditional probability. You don't use the bottom right total. You use the total from the given. You use the given event's total. Hopefully that makes sense. Now, there's also a discussion on independence. So if two events are independent, it doesn't matter if one happened. The event that the second one will occur is going to be the same. So for independent events, the probability of B given A is still going to equal the probability of B. This means that A doesn't matter. So keep that in mind, right? That's independence. So we can use this to test for independence. Okay, so this example, it says, is there a relationship between gender and handedness? To find out, we chose a random, an SRS of 100 Australian high school students who completed a survey. The two-way table summarizes the relationship between the gender and dominant hand of each student. Suppose we choose one of the students in the sample at random. Are the events male and left-handed? Independent. Justify your answer. So we are truly trying to see if there is a relationship between male and left-handed. So I want to see what's the probability of someone being left-handed given that they're male. Is that going to equal the same thing as just the probability of someone being left-handed? Does it matter that they're male? Does it influence left-handedness? Well, if they're equal, then they are independent. But if they're not equal, then they're not independent. So let's find this one first. I'll do it in blue. So that's the probability. I'm sorry. Yeah, that's the probability of being male and left-handed over the probability of being male. So let's go over here. So what's the probability of being male? So here's my males, here's my left-handed. So I have 46 males. That's my bottom number. So for this, I'm not using the total, I'm using this bottom number. And of those males, how many are left-handed? We'll find your left-handed, go over here. I have 7. Okay, and I will divide this because I need to know what it is. 0.152. 0.152. And now I'm going to find just the probability of being left-handed. This is old school. This is not conditional. We need to look at all the left-handed people, 10, out of the total. And now we do use the 100. And 10 divided by 100 is 0.1. These two numbers are not the same. So because they're not the same, these two events are not independent. And what this means is being male does have an influence on whether you're left-handed based off this data. That's what it means. So being male does influence left-handedness. Okay. So again, there was one like this on one of the practice tests, so be aware. But I like this one because it shows the difference between conditional, where you don't use the total in the bottom right corner, versus just a simple probability where you do use the total in the right corner. Okay, this rule is for independent events. So if you're trying to find the probability that A and B occur and they are independent, you can simply multiply the two probabilities. Sometimes they use this to solve for one of these, so it'd be a division problem. This can also be used to prove independence as well. And again, like I said, this can be used to show independence. This formula is not on the state test, so make sure you memorize it. And I think we made it. Slide 104. Whew, my goodness. Now, because you went through this arduous task, this terrible task, you should be well prepared for the OST to do your best. Again, good night rest, eat a good breakfast, and come here with a positive attitude. Even if you think you're going to fail, you're going to do awesome. I believe in you. All right. Good luck.